of Texas Instruments. Sharad is a lead AI engineer at Texas Instruments, where he works at the cutting-edge intersection of artificial intelligence and analog circuit design. He has conceptualized and led multiple high-impact AI initiatives, specifically targeting analog design workflows at TI, demonstrating a rare ability to bridge the gap between advanced machine learning and the nuanced challenges of analog circuit design. Sharad is also recognized as a subject matter expert in the physics-based modeling of semiconductor packages, bringing deep technical rigor to his work. Beyond his internal contributions, he plays a pivotal role in shaping TI's external technology ecosystem, where he collaborates closely with EDA vendors to evaluate, onboard, and refine AI/ML solutions, identifying critical gaps and driving the co-development of scalable, enterprise-grade tools tailored to Texas Instruments' needs.
Hello everyone. Thank you for joining for this talk. So, So I'll be talking about the IR-aware Powergrid optimization today on behalf of my co-authors here. So let's jump right into it. So what is the motivation behind this? Right? So with increasingly complex designs that we are doing in digital domain today, it becomes a long goal activity to sign off the IR drop analysis during the digital design flow. And the traditional way of fixing IR issues has multiple drawbacks. Like if the power grid itself is dense, right, and it has non-uniform PDN networks, or if there are multiple power domains, right? If there are multiple power domains, it becomes a slow and time-consuming activity to fix these IR issues during sign-off. And this fixing IR is not an isolated or siloed activity. It usually involves having to have trade-off between other design metrics like timing, congestion, DRC, and algorithm as well. So there are several techniques that are employed today for IR fixing in form of ECO strategies, but these cannot easily be generalized, and they are very customized to different designs. So and especially IR sign-off becomes more critical because of the point at which in the design cycle this is done. And at that point, the margins, the physical margins and the dynamic margins are extremely thin, and fixing any IR issues at this point will eventually lead to much bigger repercussions, where design teams have to go back to PNR and redo PNR to fix these issues. Right. So for this, we evaluated a tool from Cadence called Voltus Insight AI, which is a combination of machine learning and distributed-based optimization, which utilizes the pre-trained knowledge that it has regarding the power domain and the IR analytics to figure out what is the best way to fix an IR issue when it sees an IR issue. Well before the sign-off stage where the IR issue becomes apparent. So goes back from the PNR stage itself. Right? So there are certain design scenarios and constraints like type of power pad modeling and type of power grid management that influence how the IR issues are to be fixed while the sign-off is happening. And Voltus Insight AI allows us to actually go back and start this process preemptively at the PNR stage to start doing the PNR with that IR aware nature. Right. So any solution in this field needs to have two things. So it first of all needs to be effective in the sense that it needs to actually solve the problem, which is not cause IR violations at the end of the digital design flow. And it also has to be predictive in the sense that it should not degrade the performance of other design metrics like timing and DRC. Okay. So with that, let's see how the actual baseline workflow looks like. So this is just evaluation of baseline voltage inside tool, where we tested the tool on different types of packaging like flip chip and wire bond, and also the power managed and non-power managed type of designs. And you can see that there are three types of things that we are measuring. So what is the worst IR, what is the total IR, and the total number of violators. So so if you can see that we see that the highest number of reduction happens in the non-power managed domain for flip chip type of designs, with rest of the packages and power domains also having relatively good amount of reduction in total number of violations. Right? But you see that there is a clear distinction here with the flip chip type of designs. So like I said, related to the predictability, does it actually degrade the performance of other metrics or no? Right? So if you look at the timing analysis with WNS and DNS along with DRC, it remains almost constant across all the packaging families and the power domains. Right. So here we have some graphs which show how the instances and their IR drops vary. Right? So on the x-axis, you will see the IR drop at post-route stage, and on the y-axis, you will see the IR drop after the fix stage. So essentially after running the tool. And each of these dots represents an instance in the design. So the x equal to y line essentially says that there's no change between the fixing and the post-route stages. Right? So if you can see that for flip chip non-power managed domain, which we saw had the highest number of reductions. Right? So most of the instances and their IR drops have been brought down below this x equal to y line, which effectively says that after fixing the IR drop for all of these instances is being lowered when compared to the post-route stage. So you can also see that wire-bond power managed has very little effect. So it basically has no effect of reducing the IR on the instances. And non-power managed wire-bond has some impact, but only on the instances which have middle to lower power IR. So this becomes a critical information for us to further enhance the tool, which says that when there are power managed designs involved, the voltage inside AI is not able to optimize the IR in such a way that IR drop violations reduce. So to also improve this, we tried few custom strategies. So one of those strategies being fixing at different thresholds. So where you actually increase the IR threshold to call it as a failure and then run the tool. So the idea behind this is given higher thresholds, you will have lesser number of violations with wider margins and resources available, which would lead to better fixing rate, which indeed was true for the non-power managed designs, where you can see that as the thresholds were increased, the fixed number of violations also started increasing. So it was able to fix more number of violations. But interestingly, if you see that for power managed designs, it actually went the other way, in the sense that increasing the threshold for IR actually resulted in lower number of violations being fixed. And we also tried a different strategy called iterative fixing, which essentially is running the tool again and again at the same threshold to see if it can fix the issues that it missed out in the previous iteration. So here again we see the same pattern where the number of violations fixed actually So this also reveals a critical key issue with this automated fixing where for power managed designs it essentially says that it is ineffective. Right? So how do we tackle that? Right? So this is where we did a little bit of analysis to find out this key piece of information where in power managed designs you have switches between the main power supply, power domain, and the switch domain. Right? So when such scenarios happen, the IR drop actually is mostly dominated by the high current flow that goes through these switches which have high resistance. So what happens here is that the fixing does not take into account these high resistance switch paths. So it effectively ignores this path. That is the reason we see those IR drop instances not going down after the fixing is done. So there is also another side effect where, as you can see here, the optimization which happens in this tool that is done before the switch path or the after the switch path actually determines how good the optimization is. Right? In cases where the optimization happens before the switch path, there are scenarios where the optimization actually ends up routing more current through the switches and thereby exacerbating the IR drop that was already present on the switch. Right? So we need to address this and we need to fix around these switches in order to actually reduce the IR drop violations that were present in the power managed designs as well. So for that, we have to we work with Cadence to build a better system where the fixes happen around the switches with this context of the switch in mind. Right? So you can see that in the first picture, this is the same x and y axis. So the x-axis is post route and y-axis is after the IP fixing. So you see that there are multiple instances which are above the x equal to y line here, which are mostly switch dominated IR failures. And once this enhancement was applied, where the switch context was provided to the tool before the fixing happens, you can see those instances have come below the x equal to y line and actually had an impact on the number of IR violations. But there is still some constraint as to the tool not being able to follow the complete issue. If you see that, the reduction in the number of total violations after the enhancement is present, but it is not considerable, and there are a few reasons for that. Right? So the possible causes. So this is the summary of what we have found out. Right? So these are the possible causes for the IR drop and where the oldest tool is actually helpful. So things like sparse BG stripes or localized IR spots, long resistive paths, all of these fall under these categories where the tool is able to easily fix the issues by either reinforcing the grid with more power stripes or redistributing the current or decreasing the resistance or adding wire. But there are scenarios where there are insufficient power switches or weak power package deliveries or scarce power packs where the tool actually becomes ineffective. Right? So these are also categorized as design level bottlenecks where they can be actually mitigated by being more diligent in routing through the Powergrid. Right? So design level fixing bottlenecks can boost the solution efficacy. Right? So for example, we did a poorly planned design and a Powergrid optimized design through this tool, where we see that with the Powergrid optimization and then running the fixing, you can actually see that the number of violations were reduced much more compared to the non-optimized one. So this is the summary where you can see that the red hotspots here are on the high violation regions, and with the fixing, the violations have disappeared, and this is the stripe addition map that resulted in this fix. Yeah. So that's the